And this is our last UW Space Dialogue of the year, but we'll be back next year. And I'll just say a quick thank you to Salal Credit Union for making these all possible and supporting us. And then I will hand it to you, Sadia.
Thank you very much, Amy, and welcome everybody to the Spark Speaker Series. I'm Sadia Pekkanen, I'm co-director for Spark. And thank you, as Amy was just saying, thank you for joining us for really the final talk for this year for Space Dialogues. And I too want to thank Salal Credit Union for making this series possible, because we try to go across both technology and policy. Now, in today's seminar, we are sort of continuing with our focus on the problem of orbital debris. And to help us reflect on this from the perspective of space domain awareness, we are very fortunate to be able to bring in a longstanding member of MIT Lincoln Lab. MIT Lincoln Lab is, of course, dates back to 1951 and develops technology for defense, scientific, and industry communities with an eye on U.S. national security. Now, it's a real pleasure for me to introduce Bob Guerriero, who is at MIT Lincoln Lab. He received his BS in engineering physics from U.S. Military Academy and an MS in physics from MIT. He formerly served in the U.S. Army as Lieutenant Colonel, and he has significant depth as a space operations officer. His duties include those at the NRO, the National Reconnaissance Office, U.S. Army Space and Missile Defense Command, Army Forces Strategic Command, the National Security Space Institute, and the Multinational Corps Iraq, where he actually provided boots on the ground space support to combat operations. In short, all this means he has considerable field experience in how and why reliance on space supports ground and geostrategic operations for the United States. After several leadership positions in MIT Lincoln Lab, Bob is now the group leader of the Information, Integration, and Decision Support Group at the lab, also known as Group 93, which sounds very mysterious and exciting. And this group is cutting across both technology and policy, responsible for developing, integrating, and testing SDA tools and capabilities in order to provide support for decision makers. And he will be talking to us about R&D across the space surveillance enterprise. And with that, over to Bob. Thank you so much for being with us, and the floor is yours.
Great, thank you. Well, thank you for the introduction. Good afternoon, everyone, and thanks for this opportunity to talk to everyone. I think this is a great forum, and it'll be a great chance to just have some discussion about what's going on in the space enterprise, specifically space domain awareness. Yes, I'm at Lincoln Laboratory. I'm in the Information Integration and Decision Support Group. And we refer to it really as the Space Domain Awareness Group. That's really the bread and butter of what we do on a day-to-day basis. So I lead that group currently. I've been at Lincoln Laboratory for about 12 years or so now in a variety of roles, some on the sensor building side of things and some on the sensor employment side. And now today I find myself at the center of sort of trying to understand the data that's being collected. So, you know, I've been in the middle of this for about 12 years or so, but the laboratory has been working in the space domain awareness world for much longer than that, in fact, several decades. So that's what I'd like to talk about today is some of the involvement in research and development here at Lincoln Laboratory across the space surveillance enterprise. So I will share my screen and some slides here. Let's see. All right, can everyone see that?
Yeah, you're good.
Looks good. Okay, great. So I thought I would try to talk about, you know, part of this will be sort of a little walk through history about where we've come from and where we are today, and then part will be discussing some of the challenges we have in the space domain awareness realm today. And I'll use a very similar problem to sort of describe some of the challenges and some potential solutions. I'm going to try to talk for about 30 minutes and then we can have some discussion. But if there are questions, you know, feel free to jump in at any point as well. Okay, so I guess let's just sort of start up front and talk about what may be obvious, but some of the real challenges we have in space surveillance, and they come in a bunch of different aspects here. The first of which is there are lots of objects that we need to worry about in space. Many objects, and of course this number is growing exponentially as you're all aware, but just the sheer number of objects makes space surveillance a challenge. And then of course there's a real danger of potentially colliding with one of these objects, and at many of these orbital velocities the objects don't need to be very large for this to be a catastrophic event. So it means not only are there lots of objects to keep track of, we need to keep track of objects down to very small sizes, which itself can be challenging, especially as we talk about distances very far from the Earth. Of course, the sensors we use to do this are imperfect. They have lots of uncertainties. Some sensors have more uncertainties than others, and of course the uncertainties are in different dimensions. And then finally, there's this problem of just maintaining states when we have non-persistent sensing, which is what we find for the most part in space surveillance, is that we have sparse observations that we try to string together over long periods of time to maintain states of these many thousands of objects. So it's a tough burden, and it's increasing, and it's increasing pretty rapidly as we find space becomes much more congested. So here at Lincoln Laboratory and in many other areas across the country, there's a lot of research that's been going into trying to address this problem, and it falls in a few categories. Improving sensors themselves to improve their sensitivity and their ability to detect objects. Increasing the coverage, both spatially and in time, so that we have more persistent sensing. And then just the way we handle the data and process the data, improving those aspects as well. So I'm going to talk about some of these. And of course, it's not just Lincoln that's been working in this area. Many folks across the government and in industry have also been working on addressing these challenges. But here at Lincoln Laboratory, we've been involved in this for over 60 years. The bulk of the work we do is here in Lexington, Massachusetts. Lincoln Laboratory is part of MIT, but we are not co-located with MIT. We're about 20 miles west of MIT. And Lincoln Laboratory emerged out of, after World War II, with all the good work that MIT did to support the war effort in World War II. That was continued, and Lincoln Laboratory emerged from that. So most of us sit here in Lexington. We operate sensors all over the place. We have the Lincoln Space Surveillance Complex is in Westford, Massachusetts. That's located about 15 miles northwest of where we are now. And out in Westford, we have a number of radar systems. We have the Millstone Hill radar, which is now an L&S band radar. We have the Haystack X and W band radar system, and so you can see those here as this lovely fall picture in New England. We also operate some optical telescopes in Westford. We have the experimental test site in Socorro, New Mexico, and you can see that picture in the lower right here. It is actually right next door to GEOD Socorro. In fact, there is a very thin chain link fence that separates the two. And Socorro was the prototype for GEODs, and we still operate the experimental test site today, and we have a few meter class telescopes out there. When we operate Socorro in conjunction with the optics at Westford, we get a very long baseline here across the country, which can be useful. We're also the scientific advisors for the Reagan test site out in Kwajalein. There are a number of radar systems out there that we operate. There's the TradeX system, which is really a copy of the Millstone Hill radar. That's an L-band system. Altair is a UHF-VHF radar. And then there are a couple of imaging radars as well, a millimeter wave and a C-band imaging radar. So the point of all this is that we work very closely and we're integrated very tightly with a number of sensors. It allows us to use these sensors creatively, allows us to collect an enormous amount of data and have a very deep understanding of what goes into the actual raw data that's getting collected. Okay, so we'll spend the next few minutes here talking about what Lincoln has been doing specifically in the research and development area for space surveillance. And then I will talk about a very similar challenge to this broader space surveillance challenge that I think can be very instructive as to how we might approach this. Okay, so first, here's a plot. I'm sure you have all seen something just like this, showing the number of objects in Earth orbit over time, and this only goes up to 2018, but you get the idea. It's growing very quickly. And along the bottom are shown a bunch of efforts that the lab has been involved in to try to help in the space surveillance realm. And it's been by sensor improvements, general coverage improvements, and data processing improvements. And it starts way back here on the left in the early days with the Millstone Hill radar. And it was used, as we'll see, to track objects in low Earth orbit, including Sputnik. But this was a function of the lab's heritage, which was really in radar systems. And the lab was stood up initially after World War II to build an early warning radar system for the country. And we have a long history of radar systems. So of course, we turn those to the space surveillance problem, and that's where we started. We used Millstone to track objects in low Earth orbit, and then learned that we could track objects in geosynchronous orbit as well. And we refer to those as deep space. When we say deep space, we mean basically anything outside of LEO. And that was wonderful, but trying to detect and track objects very far from the Earth with radar systems has its challenges. It's not easy to do. In many cases, optical systems are preferred to do that. So we leveraged the experimental test site in Socorro to do electro-optical tracking of satellites that evolved into the GEODS system and then the GEODS network. We proliferated some of these sensors. So the radar systems, you saw Altair shows up on Kwajalein. We started doing radar imaging that shows up out in Kwajalein. But there are fundamental limits to what you can do with Earth-based sensors, both radar systems and optical systems. And on the optical side, it's primarily obviously limited by weather and the day-night cycle. So an obvious way to go then is, well, let's go into space. And the space-based visible sensor in the mid-90s was the first dedicated space surveillance sensor in space. Improvements continued with improved detector, improved focal planes and detectors, continued improvements in radar systems. The initial space-based visible sensor grew into SBSS, the space-based surveillance system, which eventually ORS-5 then was another progression along that chain. Larger and larger ground-based systems were built, including the Space Surveillance Telescope. And not too long ago, the Space Fence was implemented. So whole range of capability improvements. And I just want to highlight a few of these. I'm just going to cherry pick a few, and I'll talk in a little more detail on the following. So we start out with Millstone. And Millstone, the Millstone Hill radar was built out in Westford in 1957. And coincidentally, a few months after it was built, Sputnik was launched. And Millstone was able to successfully detect Sputnik within a few days of launch. And on the right, you can sort of see this was the A-scope trace from this Sputnik detection. Back then, Millstone was a UHF radar. It was upgraded in 63, it was upgraded to an L-band radar. But we realized, oh, we can use these radar systems to detect objects in low Earth orbit. And the following year, in 58, when Sputnik 2 was launched, we figured out how to actively track systems in low Earth orbit. So put an automatic angle tracking system into place. So now we can track objects in low Earth orbit. And then we realized that we could coherently integrate radar pulses and stack up many, many pulses and detect and track things that were much further away. So we learned how to track deep space targets using this technique of coherent integration. In fact, Millstone was the only deep space radar available to the country until about 1975. So this was wonderful, but Millstone and many of the radar systems that came along shortly after this, they're mechanical dishes. They're mechanically steered dishes, and they work on a task track basis. So they don't have a lot of search capability. The beams are very small, so you need to know generally where to point the radar system, which in the 50s and 60s was fine. There were only a handful of objects in space. We generally knew where to find them. So the fact that we had only a handful of sensors, a handful of operators, was no problem. There were only a handful of objects in space. But that didn't last long. And, over the last few decades, as we've said, the number of objects in space has grown very quickly. And the number, they're not all large objects. The number of small objects that we see has grown significantly. And you can see this plot on the lower left. If you're talking about large objects, and in this case, I'm calling large objects anything larger than 10 centimeters, several tens of thousands of those that we can track, that's no problem. But the 1 centimeter objects, I don't know, somewhere around 500,000, and millions of much smaller objects. And as we mentioned before, it doesn't take something very large to have a significant impact on an object in space. So we would like to understand where these objects are, but we just don't have sensors that can really detect them. So what we have defaulted to is really a statistical model of the background population. And we support NASA every year by taking some of our radar systems and just staring at selected pointing angles and detecting as much debris as we can that transits the beam. And NASA uses that to update their debris models. And that's often used as sort of a surrogate to having actual truth of where some of these objects are. And that's okay, that's good information. But what we really want to know is, where are these actual objects in space? And to do that, you can't rely on a task track system because we don't know where they are in advance. We've got to search for them. And to do that in deep space, the Space Surveillance Telescope was developed. And this is a wide field of view, high rate search sensor. There were a lot of engineering challenges that went into this because of the optical prescription of the telescope. It required a curved focal plane, which had not been developed before. So a lot of engineering marvels went into the system, but it was very successful. It was initially a DARPA project, transitioned to the Air Force, and we built it and demonstrated it in New Mexico, right next door to the GIAD site in Socorro. And here it is, you can see it in the lower right when it was functioning in New Mexico. But after the demonstration in 2017, the decision was made to move it to Western Australia. So an identical shelter was built in Australia, almost identical. The entire SST giant 3.5 meter aperture telescope was disassembled, put onto barges, sailed out to Western Australia, reassembled, and it's now actually in operation in Western Australia. It's had its, it's going through, it's just about done with its operational testing. So that's been very successful, and it's a search sensor. It can be tasked, but it's not used in a task mode. It's used in a search mode to find objects in deep space. That's wonderful for deep space. We would like to have something similar for low Earth orbit, and we do now, and that's the space fence and quadrant. And radar systems are more useful for tracking LEO objects. So this is an S-band, in this case, phased array radar now. It does uncued surveillance, puts up a fence, and here's a depiction of what that fence looks like over quadrant. It's also capable of tracking objects. It can self-cue the radar to track objects when it needs to, but it's primarily a search sensor. There have always been plans to put a second fence in Australia. It would be great. It's really not an active effort right now. But something interesting happens now when you have search sensors instead of task track sensors, and that is that when you start looking for a lot of small objects, you start to find a lot of small objects. And now this is that same plot of objects in Earth orbit, but we've expanded the y-axis, and now you can see over here on the right, these are the number of objects that we're finding that the space fence is discovering. And it's just a huge number of objects that we didn't know, we had no, ability to track before. We sort of suspected they were there through our statistical modeling, but couldn't find them. Well, now we can find them. So now the challenge has changed a little bit. There was a time when we were very data starved, and the challenge was detecting and finding objects in space. Things have switched now. We're in a very data-rich environment between data being collected by the space fence, by the Space Surveillance Telescope, by other systems like ORS-5. We have lots and lots of data. And the challenge now is not finding more things, it's what do you do with the things that you have found? And the real challenge becomes, how do you sort out the things that we should worry about from this enormous background of what is essentially debris? Because some of these things in the debris are potentially more important to us than other things. They may be more threatening to us. They may be of more concern than some other things. So I think we can say that the task track approach is pretty outdated. It worked when there were a small number of things, but today it is just unsustainable with the number of objects that are in space. Most of the objects are just uninteresting to us. We'd like to know where they are because you don't want to run into them, but we're not too concerned about them. And it turns out that when you have persistent search sensors, you actually don't need to do task track. If you're searching properly, you get all the data and you find all these objects anyway, just in the normal course of doing business. So now we've got to take a new approach and focus the resources on a small subset of the population that is very interesting to us. And that means that we need to have follow-up on the right objects. So we have to figure out which objects do we follow up on, with which sensors, and how often do we follow up. Some objects you may only need to follow up once a day, but other objects you may want to follow up once an hour. And then how do you sort out those priorities, both the priorities for observing time and priorities for processing of the data? So this is a pretty tough challenge, but fortunately, there is a very similar problem that has already been addressing this challenge, and I think we can look to them for some inspiration and some answers on how we address this. And so now we're going to talk for a few minutes about the near-Earth object cataloging problem. So, the goal here is to find and track near-Earth objects because we'd like to avoid or mitigate or maybe just warn when there's going to be an Earth impact. We've got to define a few things. So when we say near Earth object, we're talking about objects with a perihelion less than 1.3 astronomical units. Most of these are asteroids. There's a subset of these that are potentially hazardous objects. And these are the ones that are within 0.05 astronomical units. A lot of strong parallels to our space surveillance challenge. First, many objects to track, thousands and thousands. We've got to find and characterize all of them so that we can sort out this subset of the large, potentially hazardous objects that are the ones that are really of concern. There is a danger of collision with Earth. It's pretty rare, doesn't happen that often. In fact, you might say we're probably overdue for one of these. But if it does happen, it's very significant, right? So we really would like to know when we're at a risk of one of these collisions. Our sensors are imperfect. We're trying to find objects that are very far away. Many of them are dim, they're hard to detect, and there's plenty of uncertainty in where that object is and where it will be in the future. And then there's this challenge of state estimate and maintenance of those states when we have very sparse observations. Many of these objects are observed very infrequently, and we're trying to string together a state and orbit for these objects. So here's a little graphic. You may have seen this before. This is out of JPL, but this just shows the evolution of near-Earth asteroids. So this is in 1999, not too many. 10 years later, that number is growing. About 10 years later, 2018, it has grown significantly. These are the near-Earth asteroids, but then there's an even larger population of all asteroids. So many objects to sort through and try to find the ones that are important to us that we need to really focus on. Okay, so we can see how this growth of number of known objects has progressed over a couple of centuries now. Back from 1801, when the first asteroid was discovered, and at the time, these were tracked with hand-drawn maps, and there's a limit to what you can do with hand-drawn maps. So, we found first it was a handful of asteroids, a few dozen asteroids, maybe 100 or two. Then folks started using photographic methods, so now we can find and track even more objects, and that started to grow. And then we start using digital means, and of course, number of objects that we can detect and track grows significantly. This is on a log scale, so we're now in the hundreds of thousands of objects. And also plotted here, you can see the same plot on a log scale now of Earth orbiting objects. So just like we find in the space surveillance side of things, as technology has advanced, as we're able to look deeper and we're able to process data differently, the number of detectable objects increases significantly. But in this case, it wasn't just technology that drove this increased rate of asteroid discovery. In this case, it was a focused search for potentially hazardous objects. It was the realization that we've got to look for these things because we might be worried about them, and we've got to sort those out from this background of other stuff. And that started in the early 90s, the Space Guard survey, which was an initial look at, let's try to find the vast majority of these near-Earth objects that are large, greater than 1 kilometer by 2017. Some of the initial outputs of this made their way to Congress, who said, okay, NASA, catalog 90% of these larger than 1 kilometer by 2008. And then a few years later, Congress said, Okay, actually now catalog 90% of those greater than 140 meters by 2020. So this focused the search. By 2011, 90% of those 1 kilometer NEOs were found, still working on the larger potentially hazardous objects. But you can see a similar effect. You know, when we look harder, we find more and more stuff. And it's taken, in this case, a century or more, but we have cataloged now the vast majority of the near-Earth objects larger than 1 kilometer, and you can include in that population the potentially hazardous objects of larger than 1 kilometer. So it's a success story in the sense that we've cataloged most of them. It has taken a long time. In 1998, the Lincoln Linear program began, which was a part of this larger effort. And so the Linear program, Linear is Lincoln Near-Earth Asteroid Research, was one of the first big asteroid surveys. And we took the GEOD system, and I said that the ETS was a prototype for GEOD. So we had systems out there. In the mid-90s, these were upgraded from old Epsicon tubes into Lincoln back illuminated CCDs. And you can see that in this plot on the right, these are all the near-Earth asteroids larger than 1 kilometer discovered per year. Those are in blue. And then you can see what fraction of those were discovered by Linear. And so it's something, you know, almost half have been discovered by the Linear program. So it's been an incredibly successful program to detect a lot of these near-Earth objects. Now you see that has tailed off in the last decade, and that's for 2 reasons. One, because many of these have been found, so the new discoveries have just dropped off, which is a good thing. But also because we switched Linear from the ETS systems to SST in 2013, and of course that was started to be disassembled in 2017, so it hasn't been working for the last few years. And but it's back in action again. Okay, so the data gets collected, lots and lots of data now. You know, what do you do with the data? And in this case, it's the Minor Planet Center that's responsible for doing something with this data. And they're the folks who have to compile the data, designate what's of interest and what isn't, and sort out the orbits. So they catalog all of the minor planets that are discovered, but they prioritize cataloging these near-Earth objects, which really makes sense. They also, you know, provide planning and analysis tools that folks can use. So here's how their process works. There is an initial detection by, you know, some sensor gets submitted to the Minor Planet Center. The Minor Planet Center then, through this NEO confirmation page, NEOCP, then designates some of these for follow-up and publishes the ephemeris information so folks can follow up on the object. And then data is collected over time, flowed back into the Minor Planet Center with multiple sensors on multiple nights, and this is used then to get a high precision orbit on the object. So there are, you know, something on the order of 2 million observations per month that get submitted to the Minor Planet Center, 600 or so new minor planets per month. But only a small subset of these get posted to this NEO confirmation page for immediate follow-up. And so the Minor Planet Center is doing the filtering of all of these objects, and they're prioritizing which ones are most important. It's not sort of a first come, first serve thing, which is, oh, I have a new object, let's put a bunch of sensors on it to go fit a better orbit. And there are a number of tools that are available to help prioritize this. And so the new objects come in, and there's a check for, are there nearby objects? Are there nearby near Earth objects? There is a rating that's given to determine, how confident are we that this is a near Earth object or not. And this whole process with tools and checking and filtering the data is really used to just flag the highest interest objects for queued follow-up. And so this is, what we call a search nominated tip and queue process, where through search, we found some interesting things, we apply some filters, and then only forward the interesting things for follow-up. And you can look at the process like this, where this is the find, using search, the find process. We need to fit an orbit. In some cases, we want it to then track it, and then we're going to characterize it later. Like we mentioned, relies on quickly categorizing and sorting these objects, figuring out which is most important, and then applying follow-up sensors. Well, this is exactly the same process that we need to follow in space surveillance, where we would like to use our large ground-based optics to find these hard-to-detect objects. We would like to revisit them frequently. We can use space-based optics to do that. We would like to track them and better characterize them. We can use ground-based radar systems, ground-based imaging sensors to characterize them, monitor them, and assess them for their relative threat or relative level of concern. And as we move forward in space domain awareness, we should really follow this same model, and we're strong advocates for following the same model, where the goal needs to be find all of the objects. And you don't do that with task track, you do that with search, and look hard to find as many things as you can find out there. Sort out the important subset, and then prioritize them for follow-up actions, which is obviously easier said than done, but that's the prescription that we are strong advocates of. So I'll wrap up the slides here. We've been doing a lot of this work for decades. Task track had a place. It was the right answer in its day, but it's really outdated now. So we have new sensors. We have much more data than we ever used to. And now it's time to figure out what to do with that data. And we can look at other technical problems that have solved this for some inspiration. And the asteroid search and discovery area is one that has followed a similar model, and there are a lot of lessons learned there. They have been able to accommodate this rapid increase in known objects as we've been able to search for them, prioritize the importance one, and we should probably take what lessons we can from them. Okay, so I'll stop there with the slides. I'll stop sharing, and I'm happy to have any discussion or answer any questions.
Bob, thank you so much. That was a terrific overview of where things have been and where things are headed. We'll wait for some questions, but I have, as I was listening to you, I had a number of questions that I would love to have your responses to. And I think the obvious one, particularly for this audience, is it's great what you're doing. Tell us how this sort of fits into the new commercial realities where firms are also helping to provide that data. That's one part of the question. And then the other thing, sort of putting it in an international context, you sort of already mentioned Australia, but what are some of the other things that our partners and allies can do to be part and parcel of this process as well? So perhaps we can start the conversation there and then have other people weigh in as well.
Yes, two great questions. So yeah, in that whole history, I focused on really government sensors, DoD sensors, but relatively recently, there's been an explosion in commercial sensors, ground-based commercial sensors, optical sensors, exoanalytics, and
Leo Labs.
Numerica have lots of optical telescopes. Leo Labs has ground-based radar systems. There are now commercial systems in orbit that are providing data. So enormous amounts of commercial data. There's absolutely a role for them. And the challenge to us is finding the right place to use commercial sensors versus DoD sensors. And like anything else, there are pros and cons and advantages and disadvantages. You know, sometimes we find that the commercial sensors are not as sensitive as DoD sensors, which is fine. A lot of these objects in space, you don't need to be particularly sensitive to track them. Sometimes the data formats are different, data cadences and latencies are different. So all that has to be considered, but there's an important role for commercial to play. There's also an important role for international partners. You know, many of our international partners are realizing the importance for themselves of being in the space surveillance mission area. I mean, they have objects in orbit as well. They want to keep them safe, protect them from running into debris or colliding with anything else. So they're trying to get some skin in the game. Canada has, a number of space-based sensors that they that they operate that we use and get data from them. Australia has a number of systems they're interested in. Many other international partners are partnering with us to provide data, and in return, we help them piece together the full picture of what's going on in the space domain. So it's a great collaboration.
Yeah, and a very important mission area for collaboration, I think, that
Yes.
I think everybody can get on board with. I'm beginning to see some questions, Bob, so I'm going to, so this is Jacob Al-Hadif, and Jacob is a first-year UW law student. So he wants to know, what are policy options for mitigating or distributing costs caused by space debris?
Great question. And
he's interested in liability.
Yes, no, this is a great question because there is space insurance. Obviously, you can insure your payloads in space. A big part of the commercial marketplace, and the reason why there may be a business model for this is to attribute collisions in space to someone, so that then liability can be pinned on some nation or whatever. So that's part of it. I don't know. I guess there's two pieces. One is the attribution piece.
Yeah.
That's challenging. I talked about imperfect sensors and how difficult it is to stitch together an orbital state. And there's enough uncertainty that it would really be challenging to pin something on a specific object in space. I mean, we can do it, but others can make a case that says, if we say object A collided with your satellite, they can make a case and say, well, actually it was object B and it's within the uncertainty volume. So you can't say it was actually object A. So that is a problem. The other problem is, I don't know how you actually would do the compensation and what you could do with that information. And I guess that's sort of, way out of my realm. I'm as far from the law realm as you can get, I think. So I don't know what you would do with the information, but it's an important question, and it's coming up more and more as, you look at Starlink, for example, thousands of satellites that they're putting up. What happens if they collide with someone? So,
yeah,
great question.
Yeah, thank you, Bob. I have another question. This is from Ron Faith. He's asking, do you believe in the interest of sustainable space that we will continue to make progress in physical tracking, but we also need to start thinking about spectrum and perform spectrum monitoring in a similar way to SSN tracking of physical entities?
And so I'm assuming by spectrum monitoring, you mean, communications and the electromagnetics, portion of the spectrum that we use to transmit data back and forth. So if that's a wrong assumption, please let me know.
Yes, apparently that's
so-
right. Yes.
But that yes, okay. But and that is very heavily regulated now. So, you know, you have to apply for specific frequencies to transmit on, and the FCC in the US monitors that, and there are international organizations that monitor that. It's pretty heavily regulated. What we're finding is that we're starting to run out of spectrum to communicate in, and we're having to get very creative about how we combine data into the same pieces of the spectrum. There's also been, you know, there's a push to get out of just traditional the radio portion of the spectrum and get into optical crosslinks, optical downlinks. You see NASA is doing a lot of work on using optical links for high bandwidth communication. So I think that that's going to help relieve some of this pressure on the spectrum. But we're also moving away from the model. The old model was every satellite has to downlink information very frequently because you've got to keep track of what the satellite is doing. Well, that works when you have a small number of satellites. When you have literally thousands of satellites, you sort of have to move to a different model of not everyone can downlink all their telemetry all the time. So.
Makes sense. Thank you. Stan, I think you would be possible for you to ask your question, Stan.
Yeah, hi, thanks, Bob. That was great.
Yeah.
My understanding is a lot of satellites today sort of have an operational guideline that if there's a 1 in 10,000 chance of a collision, that they'll go ahead and maneuver their satellite. I'm trying to get a rough sense for if there was much better object tracking, maybe even up to continuous custody of objects. How valuable would that be to satellite operators to avoid maneuvers that they would otherwise have to spend delta V fuel, longevity, or turn off their satellite or go safe mode, reduce revenue? Have you seen any business case on how valuable that would be to, you know, substantially reduce the number of maneuvers required if you had much better tracking data?
Yeah. So I from the business sense and the numbers, I haven't seen that, but it would be very valuable just from the warning aspect, the conjunction warning aspect. So today, there are many predicted conjunctions, thousands and thousands, which don't materialize. And it's primarily because there is too much uncertainty in the way we propagate our orbits forward in time. So if you propagate an orbit forward a few days or a week, then the covariance becomes enormous, the uncertainty volume is enormous, and there's a predicted conjunction which probably will not materialize. So where we find ourselves today is there are so many warnings, people have become desensitized to them, and only in a few special cases, like, for example, the ISS is in a different category because it is so closely monitored, and people put a lot of work into making sure that we don't make a mistake there. But for most other people, they're desensitized to conjunction alerts because there are just so many of them that rarely happen. So I think much better data that is more accurate, that reduces that uncertainty volume, so that we can actually have some confidence in the conjunction alerts would be a huge advantage. Today, you don't even know what direction you should move to make yourself safer. Getting a conjunction alert, you might move in the wrong direction and make it worse for yourself.
Do you have one quick follow-up? Do you have a sense for how much space-based optical would play a role in that solution? If you imagine that you maybe have a proliferated space-based optical with maybe in a slightly higher orbit than the 400 to 600 LEO, looking down and able to provide a ridiculous amount of optical data. Does that seem like part of the solution? There's companies like Scout and Privateer and others who are starting to think about that. Is that a big part of the solution, or is that a small part of the solution?
Those geometries are pretty challenging because you're even if you're out a little bit outside of Leo, you're still pretty close, and it becomes challenging to to sort of sort out the orbit that someone's in based on the viewing geometries, and your field of view also becomes important then too. Do you have a wide enough field of view that you can actually collect data on enough of these objects? Has been a lot of discussion on sort of local awareness, satellites bringing up their own local sensors so that they can sense around in their local area, but transmit the data to a central location. So now that we have lots of data from lots of sensors, sort of like the traffic cams all over the city kind of thing. And in general, yes, I think that would help. I think more data would be helpful. It always becomes computationally difficult to start integrating and fusing all this data from different sensors, different geometries collected at different times. But we can buy more computers, and I guess we could do that if we need to. So yes, I think it would be helpful.
Great question. I want to follow up on Stan, and if people have other questions, please, by all means. Bob, thank you for clarifying that, sometimes you can have this phenomena of this desensitization of conjunction warnings. And no matter how good the technology, let me give you the other end of the spectrum. Supposing we have the perfect data, it's a perfect threat, everybody realizes it's a threat. What are our options at that point? What do we do? How do you take out the threat?
Yes, good question. So, one simple thing we could think about is, well, we just move, just move out of the way. And if you could confidently say to a satellite operator, move in this direction and you will be safer, that would be great. One of the challenges there is the timing, right? So if it is, if it's something like debris and we predicted this a day or several days in advance, we probably have enough time to figure out what way we want to move, get the commands up to the satellite and move out of the way. If the timelines get very short, that becomes a challenge. So I think that's probably everyone's first response is, how do we just move out of the way and keep ourselves safe that way? I mean, we talk about a lot of things in space, and there are a lot of objects, but space is still really big. It's relatively sparse. So just getting out of the way is probably the first thing we ought to figure out how to do.
Fabulous. Thank you. And certainly for peacetime, that kind of makes sense. If you're in a wartime situation, then probably we're having a different conversation. Thank you so much, Bob. I don't notice any other questions here. I think we're almost at time. I just want to take this opportunity to thank you for joining us and educating us about where things are headed in space domain awareness. Obviously, there's the technology sort of getting there. The policy and legal pieces also have to sort of catch up in partnership with our allies and so on, and commercial partners. Thank you very much for joining us. I look forward to having you back with us. Thank you, everybody, today for joining us as well. And we look forward to having you with us next year when we return with Spark. Have a great summer, everybody. Thank you so much.
Thanks
Bye-bye.
very much. This was great. Thank you.
Thank you, Bob. Bye-bye.